All right, so today we're going to talk about viscous flows with losses in general. So we're not going to worry about if it's fully developed. We're not going to worry about if it's laminar. Everything we're going to talk about today will work for both, right? And the first thing we're going to do is we're going to talk about some vocab. We kind of mentioned this before, but let's hit it um, more solidly. Major losses, major head losses are um, this is that's too big. Fully developed flow in pipes. And that's it. Um, yeah, that's it. Minor head losses are everything else. And this can include bends, curves, valves, entrances, exits, changes in diameter. So nozzles, right? Nozzles. Um, yeah. And as a result, minor head losses can easily overwhelm everything else in your system. Um, yeah. So if you remember, right, we did a dimensional analysis of this problem. We said 0 is equal to some function of delta P times V times D times L times some roughness times the viscosity times the density. And we found out that delta P over rho V squared is equal to some unknown function G of rho VD over mu. This should look really familiar, right? This is the Reynolds number. Some length over distance and a roughness over a diameter. And what's great is from our other modeling experience, from our experience with laminar flow, we know that this function has a particular look to it. We know that delta P over rho V squared is going to look like L over D, because we know if we double our length, we double our pressure that we need. So we know that it's a linear relationship and an inverse relationship between the diameter times some unknown function. Let's call it H now because we've taken out the L over D. So it's not the same as G, but some unknown function H times rho V D over mu and E over D. And this unknown function is our friction factor. So like I said, we can rearrange this, put a 1/2 on the bottom. So we get a delta P over rho G is equal to some unknown friction factor, which is a function of the Reynolds number and E over D, times L over D times our V squared over 2G. And this is our major head loss. Where the difficult part about major head loss is figuring out what this friction factor is. L over D is easy. It's the length of the pipe divided by the diameter, but figuring out this friction factor is not trivial. And how do we find F? Well, we use a Moody chart. So with the Moody chart, we have several steps. And I will share a Moody chart with you on Blackboard, and I will encourage you to follow along while we do this. But step 1 is going to be determine the Reynolds number for the flow. Determine the Reynolds number for the flow. And then you're going to go up, determine the Reynolds number for flow and E over D. You need both of these in order to find this. Then you're going to go find your Reynolds number and go up the Reynolds number line until you hit your E over D line. And what do we mean by that? Well, so your Moody chart is going to look like this. You have a chart. On the bottom, you have Reynolds number. And it's going to have multiple lines on it that look something like this. Like this. And these correspond to different E over Ds. So roughness over your diameters, where it's increasing as it goes up. So what you'll have to do is you'll find your Reynolds number on the bottom, and it's usually on a log scale, so you have to be careful about it, but you can find your Reynolds number. And let's say your Reynolds number is right here. You draw a vertical line for your Reynolds number. I would just draw a vertical line. That's all you do. Then you find your E over D, and let's say your E over D is roughly, let's pick a different color here, let's pick green, is roughly halfway between these two E over Ds here, right? You're gonna have to estimate. It rarely happens that you get the exact E over D that you need on this chart. And you can come up through here and you follow the general shape of these curves until you hit your Reynolds number line, and then you go straight across from that intersection. And this tells you your F is your friction factor over here. And this friction factor is usually also on a log scale. And that's how you read off your friction factor. So like I said, I'm going to publish a Moody chart online. Go ahead and find that Moody chart. And then we're going to try it together for a Reynolds number of 1 times 10 to the 5th and an E over D, which is equal to 0.0015. Okay? So go ahead, find that chart, draw your line, draw your Reynolds number line that goes vertical, find your E over D line, follow the curve of the E over D lines, right? Because it's going to follow somewhere in between. And then go up, find the intersection, go straight across to find what your F number is. And you're going to find out your friction factor is somewhere around 0.024. Cool. And we're going to practice this all the time. Oh, by the way, step 3 is go straight left at intersection of Reynolds number and E over D to get your friction factor. There's also an empirical formula. 1 over the square root of your friction factor is equal to 2.0 times the log of E over D divided by 3.7 plus 2.51 divided by the Reynolds number times the square root of your friction factor. And your calculator can solve this. It's implicit, which means it must be solved iteratively. But it's possible for your calculator to solve it. So there is also a less accurate version of this formula, which is an explicit version, which is 1 over the square root of your friction factor is equal to 1.8 times the log of E over D to the 1.11, E over D divided by 3.7 plus 6.9 divided by the Reynolds number. You know what? Let's rewrite that since it's important. I'm going to make it so you guys can read it. This is E over D, our roughness divided by our diameter. And that fraction is divided by 3.7. These are empirically found formulas, right? So both of these are empirically found. There's really no way to derive them. You just do lots of experiments and then fit these equations to them. And like I said, this is explicit, but it is, so you don't have to solve it iteratively. You can just plug it into your calculator, but it's less accurate. And this is actually the formula that's used on the Moody chart to produce all those curves on the Moody chart. So you're welcome to use either one. If you're interested, I would plug this into your calculator and learn how to use it, because it can very quickly find be very accurate, and then you don't have to worry about the Moody chart. Especially on the exam where you might have to find multiple things and print it out yourself. Now, since we're doing remotely, normally it would give you a Moody chart, but since we're remote, you might want to just learn this equation so you don't have to print out a Moody chart. For minor losses, these, like I said, these can often be the largest source of losses in a system. And we're going to, in general, we're going to define a minor loss coefficient. Minor loss coefficient, which is equal to the ratio of the minor head losses divided by v squared over 2g, which basically means that HL minor is equal to k times v squared over 2g, and it becomes a problem of finding what your minor head loss coefficient is for each particular situation. And it's going to be different for absolutely everything. There are charts and charts and charts on the internet and in your book about different situations, different, whatever the ratio is for your expansion of your pipes, the angle for your corners, including the radius of curvature for those corners. So you can have gentle bends or tight bends, right? They're all going to have different K values. Sometimes this K value is expanded on, and we get head loss minor is equal to F L over L equivalent over D V squared over 2G, where you have to look up your equivalent length. Your equivalent length. It varies based on who you talk to about how to do this. You still find your F based on your roughness of your pipe and your diameter of your pipe, but then you look up L equivalent for your 90-degree bend, for example. This actually came up recently in my life, so I was looking up. I replaced the vent for my dryer. It had gone up into my ceiling and through the floor between my attic and my first floor, and then up through the floor in my attic, and then it took 2 90-degree bends to then go out through a dormer in my attic, right? So it had to bend around a corner and do some other stuff. And what we looked up some recommended practices for dryer vents, and what they said is that dryer vents in general, the total length should be less than 25 feet. And the reason is, right, is because with major head losses, each foot adds a losses to it. So if your dryer has a certain fixed pressure that it can provide, then every foot you add is going to decrease the ultimate velocity of the fluid air moving through the vent. And the slower the air is, the more likely it is to drop lint and produce blockages, which can produce fire. So you want to keep your total length to 25 feet, but you also want to subtract 5 feet for every n number of bends, 90-degree bends. And so what this was telling me is that the length equivalent for each 90-degree bend is 5 feet, right? Is 5, which is really, really cool. That's really good to know. Yeah, it's really good to know. So that's why that makes sense, right? Is because each bend then produces as much losses as 5 equivalent feet of pipe, sheet metal piping. Yeah. Cool. Final note: the E over D, right? This is a surface roughness. And it is not what you think it is. So there are different ways of measuring surface roughness. You can take a profilometer and run it along a sample, and a profilometer is literally just like a sharp needle that then vibrates, moves up and down with the roughness, and then you can measure that changes in height, or you can do it using optically, right? There are lots of ways of measuring the variation in height of a surface. But it's important to know that E's are empirical fits. and because so literally what they did is they took this equation here, this implicit equation, and they measured the friction factor, they measured the Reynolds number, and then they said, all right, what E over D works to make this equation work? And so you have to look up these values that were fit in order for it to work well. So they'll say things like rough concrete is equal to 0.25 millimeters of roughness. It's actually more, right? Like if you look at it, it's quite rough, but when you put it into a flow situation, it turns out that that kind of roughness actually only looks like 0.25 millimeters. And that's because the nature of the roughness matters, right? Concrete has these large divots and these round rocks that come out, and so everything's actually kind of rounded. So it for rough concrete anyway, it ends up not mattering as much as something that might be really sharp. Like let's say you take the inside of a PVC pipe and rough it up with sandpaper, in which case you're going to get very sharp divots, and those sharp divots will cause much more eddies to happen when the flow flows around them, and so it'll cause much more losses. And so you can't just measure the roughness and have it work. It's actually a combination of the kind of roughness you have and the height changes due to the roughness. And so you really have to just do the experiments and solve for it, and then you get a form of roughness for that material under those conditions. It's quite tedious, but there are lots of published tables on it. And usually what will happen is if you have a material you're using an awful lot in-house or in your company, then you will do this measurement on your own, find it out as accurately as you can, right? Or you'll pay somebody to do it for you. Sometimes too, you'll most pipe suppliers will have this value handy for you so that they'll have already measured it for you, so you don't have to do it. But it's a good thing to know. All right, next we're going to do an example where we talk about minor head losses and major head losses. What we're going to do is we're going to start with start with our model, and we're going to keep adding complexity to it, right? We're going to add major head losses, and then we'll add minor head losses, and then we'll keep doing this until we figure out exactly how much H we need to supply a flow rate that we want from this pipe for like a reservoir tank with a pipe leading out of it.